Three more examples on normal tangential coordinate system. Skier is going along the parabolic path. Equation of the path is given. At point of analysis A, velocity is equal to 6 meters per second. VA, 6 meters per second. Direction will be in tangential direction, always in tangential direction. We have to find direction of its velocity in respect to x, so we have to find angle theta, this angle, and direction and magnitude of acceleration at this particular instant. We neglect size of the skier. Remember that we analyzed geometry of the motion, no forces so far. Velocity. Velocity is tangent to the path. Magnitude of velocity is given. It is 6 meters per second. Our objective is to find direction of velocity in respect to horizontal. Let's acknowledge simple relation. That velocity can be broken into two components. So velocity can be broken in x and y components. So we have motion in y direction and motion in x direction. And those two components of velocity will give us total velocity of this particular particle. Obviously, angle in respect to horizontal, this angle will be arctan of dy to dx. Basically, this is first x derivative of equation of the path. So this is equation to estimate tangential direction. And now let's take first x derivative of equation of the path. Here we go. That's what we get. Note that we are taking not time derivative. We are taking x derivative. So when we take x derivative, we get following result: 2 divided by 20 multiplied on x. We are interested in point A, and coordinate of point A is given over here. This is x coordinate and this is y coordinate. We are interested in x coordinate. That's all what we need to estimate tangential direction. X is equal to 10 meters, and that's what we substitute over here. And as a result, we get that first x derivative of the path is equal to 1. Now we have to take arctan of this. Arctan of 1 is equal to 45. Basically, this gives us tangential direction at point A. Note that at some other point we will have different result. We estimated tangential direction for this particular instant, for this particular point. Now let's focus on acceleration. We have curvilinear motion, and acceleration will have two components: tangential component and normal component. To estimate acceleration, we will need to estimate radius of this arc, of this particular arc. So at this instant, when we are at point A, there is some corresponding arc with corresponding radius and some corresponding center of curvature. So our objective is to find this radius, rho. Here is corresponding equation. We already got first x derivative. Now we have to find second x derivative. That's what we need. First x derivative was this one, this one, this one. That's what we've got in terms of x. And now we have to find second x derivative. So it would be another x derivative, and it will give us 2 divided by 20 or 1 divided by 10. I substitute this result in my equation of the radius, and that would be what? That would be rho equal to 1 plus what was our first x derivative? It was 1 divided by 10, 1 divided by 10 multiplied on 10. Multiplied on 10. X is equal to 10. Don't forget that it is squared, and we have to take 3 divided by the power 3 divided by 2 and divided by second x derivative, 1 divided by 10 over here. When you calculate, you will get 28.28 meters. That's radius of curvature when we are at point A. Now we substitute data, and that's what we get. Tangential acceleration was given, I believe. Yes, it was given. AT is equal to 2 meters per second squared, and normal acceleration is velocity squared. Velocity was given as well, 6 divided by radius, which we just calculated. And as a result of all those calculations, we get total acceleration. We don't get only total acceleration, we also get components of acceleration. So your answer can be presented in a vector form as well. So if you present it in vector form, acceleration will be equal to magnitude of tangential acceleration multiplied on unit vector t plus magnitude of normal acceleration multiplied on unit vector n. And if you want to find direction, you can find direction out of this result. Next example. In this example, we also have some motion along parabolic path. This is this equation of the path, and we know that at point A, velocity is equal to 10 meters per second, and tangential acceleration is equal to 3 meters per second squared. We have to find magnitude of acceleration when we are at this point. Total acceleration. We have to find total acceleration. So we have to find radius. We have to find radius of curvature. So this is radius which we have to find, and we need first x derivative of the path and second x derivative of the path. So first x derivative will be 0.01 x squared dx, and it will be equal to 0.01 multiplied on 2 multiplied on x, and the x is equal to 60 meters. Second x derivative will be obviously derivative of this result, and we will simply get constant 0.02. So that's our second x derivative. Now we substitute those results in our equation for radius. So here we have x equal to 60 meters, and we calculate, and we get that radius is 190.57 meters. Now we can find acceleration. Normal acceleration, velocity squared divided by radius. Velocity is given, VA equal to 10 meters per second given. given. Radius we calculated, so it gives us normal acceleration 0.5247 meters per second squared. And tangential acceleration was given. Substitute data and we get total acceleration at point A. At point A. At other point, it would be different. It would be different. It is instantaneous analysis. One more example. We have ball which is kicked with initial velocity 8 meters per second. So here is our velocity 8 meters per second and angle is 40 degrees. Launch angle is 40 degrees. Projectile motion. Find equation of the path. Find equation of the path. And out of this, find normal and tangential components of acceleration when instant of time is 0.25 seconds. We recognize that it is projectile motion, which means what? We have only weight acting on the particle, and there will be only one acceleration which is acting downwards, and it is at any point of the path. Total acceleration is known. We know total acceleration. It is 9.81 at any point of the path. That's total acceleration. So basically, if we will find tangential direction at instant when time is equal to 0.25 seconds, we will be able to break this total acceleration into two components, normal and tangential. Total acceleration. So we have to find equation of the path. We have to express y as a function of x. See, here we have y, here we have x, and equation of the path is y as a function of x. That's what we want to get. So we are going to write two equations, one for horizontal motion and the other one for vertical motion, and then put it together. I take equation number 1 and write it, substitute data. Initial condition is 0, so initial position is assumed to be 0. We put coordinate system at initial point. And then we have velocity, component of velocity multiplied on time. Component of velocity will be cosine component. So 8 multiplied on cosine 40 gives us 6.128, and this gives us equation in x direction as a function of time. So that's what we've got. That's our first equation. Now vertical motion. Vertical motion, we analyze it in the same manner. So we take equation number 3 and substitute data. Component of velocity is sine component, 5.143 meters per second. And when I substitute data, I get second equation. So initial condition is 0. Then we have component of velocity, that's VOY, multiplied on time. Then 1/2 minus total acceleration, which is acting on our particle, times squared. So we've got two equations. Now we are going to put it together and get rid of time. Get rid of time. So time will be equal to x divided by 6.128. We take this result and substitute it here and here in place of time. In place of time. After we substitute this result in our y equation, we get equation of the path, y as a function of x. Here we go. So we've got equation of the path. Now we have to take first x derivative of this equation. We take first x derivative, and that's what we get. We get following result. Now we have to substitute x at instant when time is equal to 0.25 seconds. We can easily find it. So we substitute time equal to 0.25 seconds, and we get that x is equal to 1.532 meters. So we substitute x over here, and when we substitute it, we get that first x derivative is equal to 0.4389. So now arctan of this will give us angle in respect to horizontal. So if we assume that ball is over here, velocity is acting this way, tangent to the path, that's where velocity is acting, and arctan of first x derivative will give us angle theta, angle in respect to horizontal. It gives us tangential direction. So here we go, 23.7. We found angle. Now, after we found angle, we can break our acceleration into components, normal and tangential. So if we recognize that acceleration, total acceleration is 9.81, I didn't mean it, 9.81 acting downwards, vertically downwards, we can break this total acceleration into normal and tangential directions. Angle is known, 23.7, and it gives us that in tangential direction we will get acceleration 9.81 sine 23.7, and in normal direction we get 9.81 cosine 23.7.